Good enough.
Hello, my name is Oscar Flores Gaitan. I'm a final semester undergraduate student at Universidad del Valle de Guatemala and a summer research intern at the University of Delaware. And my project focuses on disentangling planetary and stellar signals in Barnard Star. Located less than 6 light years away, Barnard Star is the second closest stellar system to the Sun and one of the most studied M-stars. It has been subject of several exoplanet claims over the years, with the most recent one being the confirmation of a 4-planet system by Basant et al. In 2025. We conducted a follow-up analysis of the planet signals using frequency domain techniques applied with NVELCH to analyze RV and AFWHM data. We modeled stellar rotation using a GP in Celerite 2, and to diagnose activity-related signals, we computed the magnitude square coherence between RV and AFWHM. We find strong coherence at the frequency of Barnard D and a nearby signal close to E, suggesting that the system requires further follow-up. Also, our Gaussian process model estimates a stellar rotation period of about 133 days. We are currently working on developing a joint Keplerian plus GP-FIT, incorporating additional activity indicators and photometric data to look for independent confirmation. You can check out the full poster by scanning the QR code, and feel free to reach out via email if you have any questions. Thank you.
Hello everyone, my name is Emiliano Jofre. I'm currently a CONICET researcher at the Astronomical Observatory of Cordoba in Argentina. Here I'm advertising a poster with early results from a program that we started a few years ago to detect and characterize transitive planets orbiting thick disk stars based on test photometry and Gemini Maroon X high precision radar velocities. In particular, we present the detection and characterization of a hot super Neptune located in the so-called Neptunian desert. This planet orbits a K-dwarf star that we identify based on both its kinematics and chemical properties as part of the transition population between the thin and thick galactic disk. In addition, we present some preliminary results on the detection of a hot Jupiter orbiting a solar-type star that unfortunately turned out to be a typical thin disk object. You can check the details at the poster, and if you have any question or comment, please feel free to contact me. Thanks.
Hi everyone, I'm Merla Philippi, a PhD student at the University of Central Florida, and I'm here to share about the work that my team and I have been working on. So I study brown dwarfs, and I've been working on modeling the atmospheric complexity and the dynamics that they exhibit. So what we're doing, specifically, we've built a grid of contribution functions for both cloudy and cloud-free atmospheres. And we focus on the L, LT, and T-type brown dwarfs. So what are contribution functions? Contribution functions, they tell us which atmospheric layers contribute most to the emergent flux and at what wavelength. So essentially they map observational features back to where they're formed within the atmosphere. So we focus on a lot of different parameters where we specifically are trying to understand the cloudy behaviors. So for example, the KZZ, the eddy diffusion coefficient, which determines how vigorously the atmosphere mixes, and the FZ, which determines how well the particles settle into and settle out of the cloud formation. So if you want to hear more about what we have and what we're finding with these, please come and visit my poster, and you can get more information about the tool that we have created and that's going to be readily available for the community soon. Thank you.
Hello, my name is Jessica Rancha, and I'm a rising fourth-year graduate student at Indiana University Bloomington. In this short presentation, I would like to introduce K2232c, a cold Jupiter that may change how we think about hot and warm Jupiter formation. K2232b, its inner warm Jupiter companion, was first discovered in 2018 and later followed up in 2021. The two sets of RV data taken, however, were offset from each other, indicating the possible existence of another planet further out in the system. After taking more measurements, we found this was exactly the case, hence K2232c. But we didn't stop there. We also looked at all confirmed cold Jupiters and hot and warm Jupiter systems to investigate their eccentricities in an effort to further understand their role in hot and warm Jupiter formation. We found cold Jupiters in hot Jupiter systems were more eccentric than those in warm Jupiter systems, leading us towards dynamically hot origins explaining hot Jupiters best. K2232 is the first of many systems in our McCAUSE survey, a mass analysis of cold and warm Jupiter systems, where we are dedicated to observing long baselines in warm Jupiter systems to find other cold Jupiter companions like K2232c. As I couldn't fit everything in this talk, I would like to encourage you to check out the rest of my poster on the workshop's website. If you have any questions about this project, the McCAUSE survey, or would like to just chat, feel free to contact me via my email, jranshaw@iu.edu, or on the workshop Slack workspace. I look forward to talking with you soon, and thank you so much.
Hello everyone, my name is Kauthar Sadi. I'm excited to share my poster titled Ground-Based Photometric Follow-up of Test Exoplanet Candidate, a case study of TOI 5956.01. So the confirmation and characterization of exoplanet discovered by the TESS mission require extensive ground-based follow-up, especially to refine transit parameters and eliminate the false positives. And this study we focused on TOI 5956.01 using photometric observation obtained with the TRAPPIST-North telescope located at the Oakhamden Observatory in Morocco. This work highlights how regional ground-based facilities like the TRAPPIST-North play a crucial role in supporting space-based mission. Not only they improve the precision of the transit measurements, but they also enable long-term monitoring and broad global collaboration and exoplanet science. Ultimately, this project shows that small telescopes and strategic location can make a big impact on our understanding of planetary systems. Thank you, and I'll be happy to discuss more details in my poster. Thank you so much.
Okay, that concludes this part. Here. Full screen. That's the first one.
Okay. Test. Okay. So, oh. Okay, hello, I'm Jang Ho-bae from Seoul National University, and today I'd like to share my work about observing transit with seven-dimensional telescope. So seven-dimensional telescope you can see in this picture is an array of 20 wide-field telescopes located in Chile. And each unit telescope can equip medium band filters with bandwidth of 25 nanometers, as you can see in these response functions. So when we observe the transit events simultaneously with the unit telescopes with the different filters, we can obtain the transmission spectrum. So when we fit the right curves from each unit, we can obtain the transit depths across various wavelengths, and this is effectively the transmission spectrum. So this configuration allows for some advantages. For example, as 7DT does not have slits on its telescope, we can select reference stars after we observe the transit. This enables more stable observation, and also 7DT also equips filter fields, so we can change the filters. So thank you for listening, and my personal number is 4. So if you have questions or discussions, feel free to come with me.
Hello, I am Joshua Bromley. I'm a grad student at the University of Toronto, and my work focuses on the relationship between gas giants and other inner companions in the same system. Now, many previous studies have explored the connection between gas giants and individual types of inner planets, like gas giants and super Earths or gas giants and hot Jupiters, but my work aims to provide a unified view of the connection between gas giants and all types of inner planets. To do this, I've assembled one of the largest radial velocity samples of exoplanets, consisting of over 1,000 planets and 600 systems. To better understand our sample and to compute good occurrence rates, I have computed completest maps for every system in my sample, and I have found that on average, for a 1 Jupiter mass planet, we are 50% complete out to about 4 AU. Now, for some high-level trends, we find that gas giants are more likely to occur in systems with other inner planets than they are to occur around a generic star. And I've been exploring further the effect of stellar properties, such as metallicity and stellar mass, as well as planet properties, such as semi-major axis, mass, and eccentricity. So if you'd like to learn more about the trends we observe and our interpretations of them, then I invite you to come by my poster, which is number 7, or to find me in person, or to reach out to me on Slack. Thank you.
Hi everyone, I'm Beatrice, a first-year PhD student at Queen Mary University of London. I'm very excited to be here and present my project on the detection of young transit exoplanet with TESS. So why we are interested in young exoplanets? As we say a lot of time this week, we know more than 5,000 of exoplanets, but just a few hundred of them are young exoplanets. Why? The detection of planets around young stars is challenging, is very difficult because of the stellar variability. But at the same time, we need to know more young exoplanets to understand how they form, evolve, and then also about their structure. So with our young stellar catalog, we are studying the stars in order to constrain the age of these stars. But at the same time, we are running 2 algorithms, YSD and Nuance, in the TESS light curve in order to detect young planets. The search is still ongoing, but we have already a list of potential new young exoplanets that we are vetting. So if you are interested to know more about my research, poster number 9. Thank you.
Hello, my name is Laura Chin. I'm a grad student at Boston University, but I actually grew up here, went to high school right across the street from Caltech, so it's great to be home. My research investigates, I guess, theoretical atmospheric demographics for rocky planets. I'm looking at what kinds of rocky planets are most likely to lose their atmospheres or hold on to them, particularly for stellar wind-mediated escape, so non-thermal atmospheric escape. This particular work that I'm presenting focuses on the core induction effect, which is basically Lenz's law for exoplanets. Come talk to me more about the physics of that. But our hypothesis is that planets with larger conducting cores may be better able to hold on to their atmospheres. So we investigate this using BATS-RS, not the official logo. And we find a really exciting trend that the atmospheric escape rate is over 2 times higher for smaller core planets versus larger core planets. And that difference actually bumps up to, I have some new results, 8 times, over 8 times, if we include more self-consistent gravity. So I'd love to talk to you more about these results. It's at poster 13, or feel free to reach out on Slack or email. Thank you so much.
Hi, my name is William Duraco, and I'm a postdoc at the University of Maryland. And I just want to introduce everyone to what I think is one of the most interesting results in exoplanet demographics from the last 5 or so years, which is the fact that ground-based microlensing surveys indicate that free-floating planets in the Earth's mass range, so planets that are unbound to any star, just drifting through the interstellar void, may outpopulate their bound counterparts by over 20 to 1. Which would actually make them the largest exoplanet demographic in the galaxy. So obviously that's kind of a staggering claim if true. And so my research has been focused on trying to address this from 2 different perspectives. One is theory. So does this make any sense from a planet formation theory perspective? And then from observation. So what will future observations by the Roman Space Telescope tell us about the origin of these worlds and the planets that they leave behind? So if any of that sounds interesting to you, please find me. I'd be happy to chat about it.
All right. Hi, everybody. My name is Ashley Elliott. I am a PhD candidate at Louisiana State University. I'm entering my final year, which means I'm also on the job market. So please come talk to me. But today I'm here to present my research. And so my research can be described by one catchphrase, which is know thy star, know thy planet. And what this means is that I study exoplanet host stars in order to study their planets. As we are all well aware, we can only know those planets as well as we know the star. And that is because almost all exoplanet properties are directly related to those of the host star. So I do this using a technique called long baseline optical interferometry. This has been mentioned actually a few times already, so I was really excited to hear that. So how this technique works is that you combine light from multiple telescopes that are separated by long distances, which results in high resolution capabilities, usually with the CHAR array, sub-milli-arc second. So I do this in order to measure angular diameters, and I can get a very precise angular diameter, which is around under 1%. From this angular diameter, we can get most of the rest of the fundamental stellar parameters, which then leads to better constrained exoplanet properties. So to demonstrate the capability of this technique, I have created an HR diagram there, which shows all stars measured with direct methods. And of course, it's an exoplanet conference, so I did highlight the exoplanet hosts. And if you're interested, you can scan this QR code. And I know I'm running out of time. I'm so sorry. And if you're interested and I've piqued your interest, please come talk to me at Poster 17, where I will tell you how I use LBOI to study the HD 219134 system. And thank you.
Do I need to advance this? Okay. Hi, everyone. My name is Caleb Parada. I'm a finishing PhD candidate at UC Berkeley, which means I am on the job market this fall. The upshot of my poster today is we're doing a precursor radial velocity survey for future Habitable Worlds Observatory target stars. Just for the newer folks in the audience, as a recap of HWO, it's a NASA mission concept for a large space-based ultraviolet, optical, and near-infrared space telescope that is going to search for potentially habitable planets and do a whole bunch of other cool astrophysics. But in order to look for habitable planets, we also need to look for regular old mass planets. And we also need to try to place limits on those planets in terms of their mass in order to inform our atmospheric models, and to inform the target list for HWO. And so in order to do this survey, I enlisted the help of about 70 undergraduate students at UC Berkeley, which was quite an accomplishment. We ended up finding a huge amount of radial velocity data spanning about 36 years. These numbers are actually out of date. It's actually more radial velocities than that now. I made these slides 2 days ago. So there's a lot more data, a lot of spectrographs. We ran all of this through an open source package called RVsearch to search for planets, refine the known parameters of known planets, and to set limits on unknown planets. So if you want to learn more about this, come talk to me. If you're interested in large radial velocity data sets, HWO precursor science, the HWO target list, things like this, come talk to me and offer me a job. Thanks.
Hi, I'm Megan Householder, and I'm also a finishing PhD candidate graduating in December. Woo! Not looking for a job though. Well, hopefully I'll get one. Depends on the funding. Okay. So I think that I'm the only laboratory astrophysicist here. Maybe is anyone else laboratory? Raise your hands. Nope. Cool. Okay. So I basically measure nanoparticles that form clouds in hot Jupiters or hot giant exoplanet atmospheres. And the way that I do this is nanoparticle synthesis and then various characterization techniques such as differential scanning calorimetry and thermogravimetry and scanning electron microscopy. And after all of this characterization, we have the surface area of these nanoparticle species. And then we do high temperature oxide drop solution calorimetry. And this is like, there are only 7 of these Alexis calorimeters in the world. And we get the surface energy after all of this amazing laboratory experiments. Now, what does this mean for all the exoplanets, okay, and the clouds? So basically, when you apply this to nucleation codes, then the surface energies, the higher they are, they drastically hinder nucleation rates in atmospheres. So here on the left, we have VHS 1256b, the brown dwarf, and silicates such as entitite and forsterite and quartz were found. And we found that they must initially condense as amorphous. And for the nucleation codes for WASP 17b, we found that basically the higher surface energies of magnesium-rich silicates hinder the nucleation rates, and that's why they saw SiO2. And yeah, if you want to know about the clouds that you guys are seeing, come talk to me. I can probably explain them. Okay, thanks.
What good luck putting the ASU people together. Hi, I'm Finnegan Keller. I'm an incoming presidential graduate assistant at Arizona State University. Let's start with a few notes. First, planet disk interactions are predicted to cause forming planets to migrate inwards towards their host star at a rate that depends on their mass. And so in multi-planet systems, you've got multiple planets migrating inwards at different rates. That in turn means that they will likely cross and capture into mean motion resonances, where the difference in their period ratios is close to an integer ratio. However, the period ratios in samples like that of Kepler don't show that all planets are engaged in mean motion resonances. Even stranger, this does not mean that resonance capture isn't necessarily a part of planet formation. Surveys of young planets suggest that the younger and younger planets are more and more likely to be engaged in mean motion resonances. And funny enough, certain kinds of resonances, so-called higher order mean motion resonances, which were predicted to be too weak to form, actually seem to be very prevalent. These situations have multiple or planets engaged such that the difference in the integers that defines the resonant configuration is larger than 1. This raises sort of an intriguing question. Is the same process, acting on these higher order resonances to form them that acts on the first order ones? And so we performed about 6,000 prescriptions of n-body integrations, or prescriptions of planetary migration using n-body integrations to answer that question. And we found, actually, I'll just stay here for a second. I can't go back. That's lovely. I'm flashing through all the slides. Bottom. Oh, there we go. Thank you so much. Yeah, but we found that, yes, indeed, this works. So if you see over on the side here, those two planets in red, and we see the period ratio and semi-major axis evolution plots are moving towards their host star, they end up in a second order 5-3 mean motion resonance, which is very exciting. Come to my poster for more details. Yeah, thanks.
Hi, I'm Chris Lamb. I'm just kidding. Hi, I'm Chris Lamb. I'm about to start my last year as a grad student at the University of Florida, where I work with Sarah Ballard. A couple years ago, John Zink et al. Came up with this really interesting result that showed a decrease in planet occurrence with increase in galactic scale height. This, among other recent results, was suggestive of the influence on the galactic environment, on planetary systems, their architectures, their occurrence, their demographics. And so in my poster, I talk about recent work that I've done modeling different changes in the planet host fraction as a function of look back time, or you can just call it stellar age. These are just some of the models that we tested. I'm just keep it simple. Sometimes we find that late time rises in planet occurrence can match the Kepler yield, and earlier time rises in planet occurrence don't match the data. There's a lot of different actual physical mechanisms that have been proposed. We're working with galactic dynamicists, been an enriching experience, and I'd love to talk to you more about that. Thank you.
Hello, everyone. I'm Lin Honglin from Zhejiang University, a PhD student. So what I'm doing is a theoretical work on the dynamics of a planet pair migrating in a gas disk. You all know the mean motion resonance already, which means that the period ratio of a planet pair is J to J minus K, for example, the 2-to-1 or 3-to-2 mean motion resonance. And the planet can migrate in a gas disk. The previous work have showed that the convergent migration can lead to mean motion resonance trapping, which means, for example, the outer planets migrate faster than inner, then the distance of planet pair become closer, and finally they will be captured by mean motion resonance. So in our work, we treat the migration timescale tau A and the eccentricity damping timescale tau E as a free parameter and see what's the different outcome of a resonant capture is. So here are our key results. You see, well, we divided this figure into different colored region, and the colored lines are our analytical criterions of this. So the two results is that the migration trapping requires the weak damping and the slow migration. And after the planets have been trapped, the stability decreased as the ratio of tau tau E decreases. For more details, come to my poster 36 or just talk to me. Thank you.
Hello, my name is Patrick. I'm a graduate student at Johns Hopkins University, and this is kind of a plea to care about the star that your exoplanet orbits. With the recent release of SDSS 5 data, data release 19 was recently released, it shows a large dispersion in abundances of host stars. You can see these two plots here. I have metallicity on the x-axis and CO ratio or NO ratio on the y-axis. There are two solar composition dots in the center of these plots right here, and then a few exoplanet hosts overplotted. And so what my work entails is taking solar type JWST host stars or host JWST target host stars and characterizing their temperatures, surface gravities, metallicities, and abundances as accurately and precisely as possible using spectroscopy from, say, Espresso and photometry from a whole host of sources. These yield precise stellar parameters and abundances, as well as stellar characteristics like effective temperatures and radii that are consistent with interferometric measurements that have been done on, granted, not many exoplanet hosts, but of those that have been characterized. It's consistent. So thank you.
All right. Hi, everyone. My name is Brandon Radzum, and I'm a PhD student at Indiana University. I'm also on the job market in the trenches right now, so pay attention. So I'm presenting some of my work on stellar obliquity, which is the angle between the orbital axis of a planet and the stellar spin axis of its star. And so we've observed large spin-orbit misalignments for planets like hot Jupiters and sub-Saturns, which is often interpreted as evidence for high eccentricity tidal migration. However, the primordial spin-orbit distribution of these types of planets, which we take for granted as being aligned, has actually not been directly constrained. And recent evidence for primordial misalignment, such as tilted protoplanetary disks, kind of challenges our assumption that the planets are born that way and that this misalignment is nurtured. So key to this investigation is the fact that compact multi-planet systems can actually act as a reliable tracer of the primordial disk plane due to their dynamically pristine configurations. So thanks to TESS, now there's a sufficiently large sample of hot Jupiters and sub-Saturns in these kind of compact configurations. So what I did is target these systems with the extreme precision Newid spectrograph to measure their obliquity angles. And what we found is that these hot Jupiters and sub-Saturns are well aligned, which kind of points towards the fact that, hey, they were probably born that way. So this provides renewed evidence for high E migration while simultaneously showing us that some of these planets, even hot Jupiters, have to form quiescently because they're aligned. And if you're interested to know more, I have a poster and I have a couple papers on this topic. So thanks for your attention.
Hi, everyone. My name is Sheila Sager. I'm a final year PhD student at the University of Florida, and I'm primarily interested in probing the orbital dynamics of small planets around small stars, namely early to mid M dwarfs, which, as we've heard this week, is the predominant rocky planet host in our galaxy. And I do this within a demographic lens using information we can obtain from large-scale transit surveys like Kepler, TESS, and K2. And we can't, unfortunately, constrain eccentricities very precisely for individual planets using only transit light curves. But what we're doing is combining all the information we have for all the planets within a Bayesian hierarchical framework, which really highlights the power of a demographic lens, in my opinion, in a really beautiful way. And we can do this to identify trends, large-scale trends in the population of planets and their eccentricities. So the result that I'll talk about in my poster is that we find that very large planets, sub-Neptune plus sized around M dwarfs, have significantly higher eccentricities than small planets around M dwarfs, which suggests that there may be two distinct formation and dynamical evolution mechanisms that dominate for these two types of planets. We explore what this might mean for formation and evolution, and also the role of the galactic context. So things like stellar flybys, galactic height, stellar ages, things like that. So please come find me if you want to talk about this, or look at my poster. It's near the back of the tent. Thank you.
Hello everyone, my name is Ritika Sethi. I'm a PhD student at MIT. Recently, I've been looking at planets with high spin orbit misalignments. And if the misalignment is around 90 degrees, they are called polar planets. And these are interesting because we would expect planets to be born aligned because we think they form in protoplanetary disks. So there are several dynamical theories which have tried to explain these misalignments post-evolution, like Kozyledov oscillations and planet-planet scattering. And both of these processes not only excite a planet to a misaligned orbit, but also eccentric orbits. And if these processes are really the reason behind these misalignments, we should see evidence of these processes in the physical properties of the planet, because the eccentricity is followed by tidal dissipation, which would generate internal heat in the system, cause tidal heating, and this leads to, there was an animation showing the planet just inflates. So this leads to the inflation of the radius of the planet. And to check that, we created a sample of misaligned and aligned planet populations, and we did find that misaligned planets are in general more tidally inflated than aligned planets, with some statistical significance. For more details, come check out my poster, or you can also check out my paper. Thank you.